Hello, welcome to a new tutorial on chemical equilibria presented by ESHRDB with reference Cambridge International AS of Chemistry by Laurie Ryan and Roger Norris. This is a tutorial on equilibrium. So this equilibrium can be is both chemical equilibria and acid-base equilibria. So let's start. The learning outcome here is going to explain what is meant by reversible reaction and dynamic equilibrium. State Le Chatelier's principle and apply it to deduce qualitative the effect of change in temperature, concentration, and pressure to the system. State the changes in temperature, concentration, deduce expression of equilibrium constant in terms of Kc and partial pressure. So this is where we have this one. We have calculate the value of equilibrium constant in terms of concentration. We have describe the conditions we use in Haber process and contact process is going to still involve this one, and this is the last one, which is Bronsted-Lowry theory of acid bases. We are going to do it in acid-base equilibria. So now let's see this definition. We have reversible reaction equilibrium. You need to know that a reversible reaction is one reaction that is occurring in both directions. Example, if copper sulfate plus this is capable of occurring back in the opposite direction. So you have it. So this is actually a reversible reaction. A reversible reaction here can also occur in this both direction. And now we need to know that the reversible reaction are reaction which can occur in equilibrium. That is, at the end of the reaction, you have hydrogen, you have hydrogen, and you have hydrogen iodide being found inside the mixture. So this is what is being said to be in equilibrium. That is, in equilibrium, you need to know that in chemistry we have the reaction usually occur in dynamic equilibrium. That is, the rate of change of the reactant to product is equal to the rate of change of product to the reactant, and all of them exist in the same mixture. So that's said to be dynamic equilibrium. So characteristic of equilibrium is dynamic. The forward and the reverse occur at the same rate. The concentration of the reactant and product remain constant at equilibrium and require a closed system. So if you don't have a closed system, then the reaction can never be in equilibrium. So let's define what is a closed system, an open system, and then an isolated system. A closed system is one which is where the matter does not move in and out from the system, but energy can be exchanged in the system. So that's the first thing, closed system. The next one is the open system. Open system is a system which is both open to energy and matter. And lastly, we have isolated system. Isolated system is one which is neither open to energy nor there is no exchange of energy with the surrounding, nor exchange of matter with the surrounding in an isolated system. So this is a different definition of system that you have to put in mind. So now the forward and backward, so you have different explanation for that. So now you have equilibrium required in this closed system as such here. So if you have an open system, all of them is going to occur in the forward direction, while if you have a closed system, it's going to be in equilibrium. So you have changing position of equilibrium. So we have the position of equilibrium is going to be considered when using the Le Chatelier's principle. So you have position of equilibrium to relative amount of product. We have system is disturbed, so change in temperature and product. So we need to know that the position of change in equilibrium can be changed to three main factors. We have the concentration, we have the pressure, we have the temperature, and we have the volume. So these are the four main factors which are going to change the equilibrium position. And the fifth factor, which is actually the catalyst, does not change equilibrium position, but instead increase the rate of reaction by providing an alternate route to the reaction where the activation energy is going to be lower, but it does not change the equilibrium position. So catalyst has no effect on the change in equilibrium position. So let's say Le Chatelier's principle. Le Chatelier's principle states that, so if you have any factor, so Le Chatelier's principle said that the equilibrium position is going to move in a direction such as to oppose to the change producing it. So if you have a factor that is going to cause the movement of a certain reaction, Le Chatelier's principle is going to oppose that factor. So let's see how Le Chatelier's principle is going to act. So the first thing in this reaction of ethanoic acid ethanol to produce that, so we see that the concentration, if you increase the concentration of ethanol, in order to reduce the concentration of ethanol, the reaction is going to be moving in the forward direction. So that's by the Chatelet principle. If you increase the concentration of ethanoic acid, in order to reduce the concentration of ethanoic acid or oppose that change, is going to move in the forward direction. If you reduce, if let's say if you increase the concentration of ethyl ethanoate, in order to oppose this change, or in order to reduce the ethyl ethanoate, the reaction is going to move backward. And lastly, if you reduce the concentration of ethanol, in order to oppose, that is increase ethanol, the reaction is going to move still backward. So these are the points to put in mind. So now, after visualizing the Le Chatelet's principle, so we also the Le Chatelet's principle considered in cases of gases. So we have in case of gases, let's take an example of sulfur dioxide plus oxygen, and we consider the pressure and volume. We need to know that at the position where the stoichiometry is going to be high, let's say 2 here, 2 plus 1 is going to be 3, and here is 2. Here is going to have a higher volume compared to this one. So let's say that we reduce the volume of the mixture. If you reduce the volume of the mixture, it is going to go toward the direction of this one. So if you reduce the volume, the reaction is going to move forward and is going to oppose that change, that reduction in volume, and produce sulfur trioxide. If you increase the volume, the reaction is going to move backward and produce more of sulfur dioxide plus oxygen, in order to occupy more the space and to reduce the change producing it. And now if you increase the pressure, it's going to move forward in order to reduce the pressure that is producing it. And if you reduce the pressure, it's going to move backward in order to increase the pressure of the walls. So these are the different points, or the increase the change producing it. These are the different points involved in Le Chatelet's principle. The last one, you need to know the equilibrium law. Equilibrium law is stated as, so this is the formula for equilibrium law. But in order for us to have this formula of equilibrium law, you need to have a statement of equilibrium law. It is stated as in a reversible reaction. So equilibrium law states that in a reversible reaction, equilibrium constant is given as, so in a reversible reaction, the product of concentration of product raised with the product of concentration of product divided by the product of concentration of reactant raised with appropriate power is a constant at constant temperature of 298 at constant temperature. So that's the equilibrium law, and that constant is the equilibrium constant, and this equilibrium constant is given as the product of the concentration of product divided by the product of concentration of the reactant, all raised to the appropriate power. In this reaction, let's say in this reaction of hydrogen plus iodine to give hydrogen iodide, you are going to have the concentration of the product here, which is concentration of hydrogen iodide raised with appropriate power, raised to the power 2, divided by concentration of hydrogen raised to the power 1, which is 1 stoichiometry here, times concentration of iodine raised to the power 1, which is 1 stoichiometry, and your answer is going to give you the answer. So you need to know that the the expression of the unit of the equilibrium constant vary with respect to your equation. In this case, you have mole per dm cube squared, all squared, divided by mole per dm cube by mole per dm cube. So here is going to be unitless. So these are different points. So let's say the expression is going to be given as Kc is equals to, let's say that the product is C and D, and the appropriate power respectively P and Q. We are going to have C all raised to the power P, D all raised to the power Q. We are going to have A all raised to the power M and B all raised to the power M. All that you have the appropriate power, and you have your answer. So these are the different things that you have seen in chemical equilibrium, and you can say thanks for your kind attention. And last point you have to visualize on chemical equilibrium actually is equilibrium expression involving partial pressures. You need to know that we also have another equilibrium expression involving partial pressure, where we say that it's equals to the equilibrium constant with respect to partial pressure is defined as the partial pressure of the product raised to the appropriate power divided by partial pressure of the reactants divided by the product of the partial pressure of the reactant, all raised to the appropriate power. Example, here you have 2 as appropriate power. You have partial pressure of 2 divided by partial pressure of n times the partial pressure of 3, all that. So these are the different partial pressure. I'm going to have Kp, and you have a relation between Kp and Kc, and that relation is Kp is equals to Kc all into RT raised to the power delta n, where delta n is actually the change in number of mole from reactant. So number of mole of reactant minus number of moles of number of moles of product minus number of moles of reactant in a well balanced equation. That's a trigonometric equation. So this is what was involved in chemical equilibrium. So say thanks for your kind attention. Please don't forget to like and subscribe for the channel. Thank you.